All right, let's dive in and crack open the tiny little computer brains that pretty much run our entire modern world. I mean, think about it. They're in everything. And today, we're going to figure out exactly how they work by imagining we're building a smart device from scratch.
Seriously, have you ever stopped to think about how your fitness tracker knows your heart rate? Or how a little weather station can predict rain? They all sense the world, they think, and they communicate. And, at their very core, they all rely on the same fundamental building blocks that we're about to explore.
So, to make this all feel real, we're not just going to sit here and talk theory. No way. We're going to frame this whole explainer around a really practical challenge. What does it actually take to build a smart device?
So here's our mission. We're going to build what's called an edge data logger. All that means is it's a little device that can sit out there in the real world, at the edge, and do three key things: sense what's going on around it, process that info, and then store it. It's the perfect little project to pull back the curtain on how these things really work.
Okay, so what's the very first thing our data logger needs? Well, it needs a brain, right? And in the world of smart devices, that brain is called a microcontroller.
A microcontroller, or MCU for short, is just a marvel. It's not just a processor. It's an entire computer system. The processor core, the memory, all the connections to the outside world shrunk down and packed onto a single tiny chip. It's the self-contained command center for our entire device.
Now, what's really fascinating is that even though there are tons of different microcontroller brands, a huge number of them actually use the same engine inside. For our project, that engine is the ARM Cortex-M4. ARM designs the core processor, the brain of the brain, really, and that little M tells you it's made specifically for microcontrollers.
And this gets to a really key point about how this whole industry functions. ARM doesn't actually make the physical chips, they're an architecture company. They design the blueprints. Then, companies like ST Microelectronics come along, license that Cortex-M4 design, add their own special features around it, and then a foundry like TSMC actually manufactures the silicon. It's this business model that has allowed ARM's designs to end up in billions and billions of devices.
So why is this ARM design so darn popular for small devices? It really comes down to its architecture, which is called RISC. Now think of it like this. The processor in your laptop uses CISC. That's like having one complex kitchen command for make a latte. But RISC, which ARM uses, breaks it down into simple, fast steps. Get milk, steam milk, pull espresso shot, combine. Each step is tiny and incredibly efficient. That means the processor itself can be simpler, which means it uses way less power, which is absolutely perfect for a little battery-powered gadget like our data logger.
Okay, so our data logger officially has a brain. But a brain on its own is kind of useless, right? It needs senses. It needs a way to actually know what's happening in the physical world. And it does that with a special piece of hardware called an analog-to-digital converter, or ADC. See, the real world is analog. It's a smooth, continuous flow of information, like the temperature slowly rising. But our microcontroller brain, it only speaks digital. It only understands ones and zeros, clean numbers. The ADC is that crucial translator. It takes that messy analog reality and converts it into a precise digital value the brain can work with. It's literally the MCU's sense of hearing, touch, and taste, all rolled into one.
And the way it works is just brilliant. Let's follow a signal. First, a multiplexer acts like a switch, choosing which sensor to listen to right now. Then, a sample and hold circuit takes a super fast snapshot of the voltage from that sensor and holds it steady. Then the real magic happens. The converter rapidly guesses and checks to find the perfect digital number that matches that snapshot. Finally, that digital value, in this case a 12-bit number between 0 and 4095, gets put in a register, ready for the brain to use.
So we can sense the world. Check. But our data logger has to do things on a schedule, right? Like maybe we want to take a temperature reading exactly every 5 minutes. For that, it needs a rock-solid sense of time.
And this is where timer peripherals come into play. Look, if the processor is the brain, you can think of the timers as the system's heartbeat. They are incredibly precise little hardware modules that just sit there and count. And by counting, they allow the MCU to schedule tasks, create perfect delays, and generate control signals without the main brain having to constantly check its watch.
And they are so much more than just a simple stopwatch. They're these super versatile Swiss Army knives. They can generate a perfect 1-second tick. They can create complex signals to dim an LED or control a motor. They can measure the speed of a spinning fan. They are truly the unsung heroes that make real-time control possible.
All right. Our device is getting pretty smart. It can sense the world and it can act on a precise schedule. But it's not an island. It needs to talk to other chips on the board.
like, say, the memory card where we want to store all this data.
To do this, our microcontroller needs a voice. And in electronics, that voice comes in the form of standardized communication protocols. You can think of these as the languages that different chips agree to speak so they can understand each other without any confusion.
Let's take a really popular one called I2C. It only uses 2 wires, which is awesome. The master device, that's our MCU, kicks things off with a start signal. Then it shouts out the unique address of the slave device it wants to talk to, like a specific sensor. That sensor hears its address and says, "Yep, I'm here." Then they can exchange data back and forth, and when they're done, the master sends a stop signal. It's like a tiny, super efficient and organized phone call between chips.
And I2C is just one of the languages our MCU can speak. It's got a whole vocabulary. For something that needs more speed, like writing to an SD card, it might use SPI, which is faster because it uses more wires. And for something where reliability is everything, I'm talking about the brakes in your car, it uses an incredibly robust language called CAN. It's all about having the right tool, or the right voice, for the right conversation.
Okay, we've met all the key players now. We've got the brain, the Cortex-M4, we've got the senses, the ADC, we've got the heartbeat, the timers, and we've got the voice, the communication interfaces. So now let's put it all together. Let's follow a single piece of data on its journey through our edge data logger.
Okay, step 1, acquisition. It all starts with a sensor out in the world, let's say a humidity sensor. It measures the moisture in the air and creates a raw analog voltage. That signal goes straight to the microcontroller's ADC. It senses, which translates it into a digital number the MCU can actually understand. Next up, step 2, processing. The Cortex-M4 core, our brain, grabs that raw number. Now it can get to work. It might clean up any noise in the signal, convert it to a useful unit like % humidity, and then, this is crucial, it uses a timer, our heartbeat, to attach a precise timestamp. Now we don't just know the humidity, we know exactly when it was measured.
Step 3 is storage. We have this perfect, processed, time-stamped piece of data. We can't just let it disappear. So now the MCU uses one of its voices, the fast SPI protocol, to have a quick conversation with a micro SD card and save that data point for later.
And finally, step 4, communication. Our logger doesn't just have to hoard data. Maybe once an hour, the MCU can wake up, look at all the data it's collected, create a little summary, and then use another one of its voices to talk to a Wi-Fi or cellular module and send that report up to a server in the cloud.
And really, that's it. The processor, the ADC, the timers, the communication interfaces, these aren't just random technical terms. They are the fundamental building blocks. They're like digital Lego bricks that engineers snap together to create every single smart device you can think of, from a smart thermostat to a satellite. So, now that you know what the pieces are, what would you build?